All right, everyone, let's take a look at this tool here that can help us visualize some exponential functions, okay? So we've got this graph here. As you can see on our left, we have the general form of our exponential function. That's going to be a times b to the x power, right? And we've got this guy here, a equals and b equals. It's just a tool that lets us adjust different values of a, our initial value, or y-intercept, and different values of b, our ratio, and it plots the function for us so we can see how it looks, okay? So we started with a pretty simple one here where a is going to equal 1 and b is going to equal 2. So that means we've got a ratio of 2 and a y-intercept of 1, as we can see here, right? Here is a y-intercept of 1, and the ratio 2 means that we're going to be multiplying by 2 over each interval of x, right? So x equals 1 means we're at 1 times 2 to the first power, right, which gets us 2 as we expect, right? X equals 2 gives us 1 times 2 to the second power, right? 1 times 2 squared equals 4, right here as we expect, right? So it's a nice tool that lets us visualize. It looks like we expect, right? It has our a-intercept, our y-intercept at the value of a. Like like most exponential functions, all exponential functions that have a positive y-intercept and a ratio greater than 1, it grows very, very quickly as values of x increase, right? If I zoom out a bit, we can see even how quickly it grows. Like, look at that enormous level of growth once you get into larger numbers of x. Once you get to like x equals 100, I mean, you're hardly going to be able to zoom out enough to even see how large that value is going to be on the y-axis. That's just how fast these things grow, okay? All right, let's play around with these values, see what we get. See if we have a bigger value of a, right? We can adjust our value of a. That's always the y-intercept, right? A equals 2, we can see our y-intercept is at 2. A equals, let's say, 4, we can see our y-intercept is at 4, right? And of course, that means the function's going to grow faster. But what makes a function grow even faster, let's go back to a equals 1. What's going to make a function grow even faster than changing a is when you're going to change b, right? Change the ratio. Change the ratio a little bit and look how much faster it grows, right? Change the ratio to b equals 4. It grows incredibly fast. Let me zoom out a bit. Rather zoom in. Maybe it's better to zoom in, actually. Let's zoom in. See, when you're at x equals 1, you're already up at y equals 4. If we change b to a huge number, right? I mean, look, if it's at something like 14, multiplying by 14 over and over again, it's going to give you a huge, huge output, right? See that? Very, very high number. And then if we increase a even a little bit, right, the function just gets enormous, right? All right, it's just good to be able to play around with this tool, get a sort of intuitive idea of how exponential functions work. Let's look at exponential decay, right? Actually, here's something we should look at that's interesting. Even if you have a super small value of a, right? Like a equals 0.01. So we're starting out with a very, very small number, right? And even if you have not even a huge value for b, let's say something like 1.5, right? Okay, something like this. All right, we have a really small number for our initial value. We have a pretty small value of b, a pretty small common ratio. So it starts off not growing really quickly, right? But let's zoom out. Even with very small values of a and very small ratios, as your inputs increase, as the x input increases, even still, exponential functions grow so quickly that even with these small positive values of a and b, for large values of x or larger values of x, the value of the function of the output on the y-axis still grows incredibly quickly. See that? So let's also remember a little bit about exponential decay. Let's pick a pretty large a value. Let's pick 10. Can we get up to 10? Let's pick a equals 10, okay? Remember what exponential decay is. Exponential decay, is when you have a positive a value, but a positive b value less than 1, something like 0.4, something like 0.4, okay? So look, the value of a, that's still the y-intercept, right? If a is equal to 10, the y-intercept is still at 10, right? But in this case, we are decreasing as the value of x increases, right? This is exponential decay, where your ratio is a positive number less than 1. You're multiplying by a number less than 1 over and over again. That's going to shrink your value. It's going to stay positive, but if we look here close to the x-axis, right, it's going to get very small. See, it's going to get very small very quickly, right? And of course, when you're dealing with exponential decay, the function grows very quickly to the left of the y-axis, right? So let me enlarge my recording screen a bit, or maybe move it over so that you can see this tool here to your upper right that I'm using to zoom in and out. We have this tool to our left. It has our exponential function in the general form, and then these tools that you can control for different values of a and b. So your next couple questions, I'm just going to ask you to use this tool to investigate some different properties of exponential functions.